Good morning, my dear friends. I hope you all are doing great. Today, I have come up with a topic called as entropy. The symbol of entropy is S, my dear friends. What is this entropy all about? Let us understand, my dear friends. Entropy is a measurable physical quantity associated with a state of disorder. This is important here. A state of disorder. You can say or randomness or uncertainty, my dear friends. So let us understand it by giving an example, my dear friends. Let us suppose in a particular classroom, okay, teacher is there, okay, and teacher is giving a lesson to the students, correct? And students are sitting at their respectable, places or at their respected places, correct? So there is a discipline in the class when teacher is present in the class. Every student is sitting at their respected places. So complete perfection is there in the class. There is a complete order in the class. There is a complete discipline in the class in the presence of a teacher. So that means that disorder in the class is almost negligible, my dear friends. Yes? Now what is my point? If we let the teacher to come out of the class, teacher has come out of the class now. Now students are free. Nobody is there in the class. Now students can move from one corner of the class to the other corner, or they can come out of the class. So that means now there is no discipline now. Students are free to move. They can go anywhere now. That means that disorder has come into action now. Now the students are disordered now. But when teacher was there in the class, there was a perfect discipline, there was a perfect order in the class. But once the teacher has come out of the class, some people are moving left, some are going right, some are going to the corner, and some are coming out of the classroom. So there is a complete mess. There is a complete disorder, my dear friends, in the class now. So that is what we call as entropy. Entropy is related to the disorder, my dear friends. If I give you just a simple example, if you take on solid and you take on liquid, my dear friends, and you take on gas, everybody is aware about this factor that in solids, particles are very close to each other, my dear friends. So there is a perfect discipline, there is a perfect arrangement, there is a perfect order of the particles in the solid, my dear friends. So entropy will be very, very less. Entropy stands for what? Disorder. Disorder is very less in solids. But now look at the liquids, my dear friends. They are little far away from each other, little far away. So they are little bit free to move. These particles in the soft liquid can move much faster than the solids. Here in the solids there may be a vibration of the particles, but in liquids there is a movement of particles. They can move from one place to another place because they are little free as compared to the solid. So the disorder has increased. Now look at the gas, my dear friends. These particles are free to move. They can go anywhere, my dear friends. So now tell me, in which case, what is the intermolecular force of attraction? Order of intermolecular force of attraction, I will tell you. So if I tell you order of intermolecular forces, yes? So highest intermolecular force will be in solids, then liquids, then gases. Let us see the order of kinetic energy, my dear friends. Tell me in which case particles are free to move. The particles are free to move in the gaseous state. So gaseous state will have the higher kinetic energy, my dear friends. So order of kinetic energy will be like this. Solid lesser than liquid, and liquid less than gas. So kinetic energy is highest in the gas, my dear friends. So when the kinetic energy is highest in the gas, that means particles are free to move. So the disorder will be more, my dear friends. So in case of a gas, if we talk about here, the kinetic energy of molecules is more. So obviously the disorder will be also more. Disorder is also more. So now, my dear friends, what is the order of entropy, my dear friends? We know that here kinetic energy increases, disorder also increases. So kinetic energy is directly proportional to disorder. So I will write down the same thing here. It will be solid, liquid, and finally the gas, my dear friends. So please remember, my dear friends, that the gases will have the highest disorder because gaseous molecules have high kinetic energy and they can easily move from one point to another point. They are free to move and they will mess up the things. They will create the disorder, my dear friends. And remember, when the teacher is present in the classroom, everybody is sitting at their own places. That means there is an order. Yes? So entropy will be very less. But once the teacher comes out of the class, students can go anywhere. That means disorder will increase, my dear friends. Remember that particular point. Just have a look right out here and mention these things. Dear friends, let us talk about now entropy change, my dear friends. What will be the entropy change? Entropy change can be represented as delta S. That is called as change in entropy. If I take any chemical reaction, my dear friends, and I can tell you that whether the entropy of that reaction is increasing or the entropy of that reaction is decreasing. Let us have a look, my dear friends. If delta S, this one, is positive for any chemical reaction, or if it is negative for any chemical reaction, then what is the meaning of this? If it is positive, then obviously entropy, okay, during a chemical reaction increases. If it is negative, my dear friends, it means entropy during a chemical reaction decreases, my dear friends. Let's take on this delta S first of all here. Usually you were writing this expression delta H, that was enthalpy change, was equal to enthalpy of products minus enthalpy of reactants. We have already discussed this expression, my dear friends. In the same way, if this was a state function, my dear friends, state function for a chemical reaction, this guy is also a state function. This is a state function. So enthalpy change is a state function and entropy change is also a state function. So it will be equal to Sp minus Sr. That means entropy change delta S, which is a state function, is equal to entropy of products minus entropy of reactants. Now if we have this expression with us, my dear friends, if entropy of products, we call it as entropy of products, and this is your entropy of reactants, and this term is your entropy change. So it's a state function. It depends upon final and initial value, my dear friends. Initial means reactants and final means products. Now from this expression, if the value of delta S is positive, what is the meaning of this positive value, man? It means that entropy of products is greater than entropy of reactants. Then only delta S will be positive. So I will write down here, entropy of products is greater than entropy of reactants, my dear friends. Now here delta S is negative. What is the meaning of negative here? That is entropy during a chemical reaction decreases, my dear friends. That means out of Sp and Sr, which value is greater? This negative value is greater. That is the entropy of reactants is greater. That means entropy of products is less than entropy of reactants, my dear friends. When this situation is there, my dear friends, we will tell that the delta S value will be minus. You can replace this small r by capital R also, does not matter. Okay. So now here you have learned that in any chemical reaction, delta S can be either positive or it can be negative. When delta S is positive, understand that entropy of products will be greater than entropy of reactants. And when delta S is negative, understand that entropy of products will be less than entropy of reactants. If you take a simple example here, my dear friends, let me take one chemical reaction here where the entropy of products should be greater than entropy of reactants. A general reaction we will take. Let us suppose we will take AB. AB is just a solid. And we will break this AB into A gaseous and B gaseous. Now here we have solid. The entropy will be very less here. And this is your reactant. And these are your products. I told you last time, what is the pattern of the entropy? It's like this. So who has the highest entropy? Gas. So you are moving from solid to gas. That means entropy is increasing, my dear friends, here. So when you move from solid to gas, entropy will increase. Who will have greater entropy? Products will have more entropy than reactants. Because products are gaseous and reactant is solid, my dear friends. That means products will have more entropy than reactant. That means Sp will be greater than Sr. Yes, my dear friends. Let us take the reverse of this, my dear friends. The reverse will be A gaseous plus B gaseous will give me AB. And AB is solid. And this is your product here. And these are your reactants. Reactants are gaseous. So entropy will be very high. And product is solid, so entropy will be very less. That means the entropy is decreasing from reactants to products. That means who will have the greater entropy then? Reactant has higher entropy because it is solid, it is gaseous, and product will have less entropy because it is solid. So greater entropy is for the reactants, my dear friends, because reactants are gaseous. So I will write down here reactants are gaseous here for this and product is your solid here. So reactant will have greater entropy because it's gaseous and product will have lesser entropy because it is solid. And in this case, my dear friends, here the reactant is solid, and here in this case the products are gaseous. So the entropy of the products will be greater than the entropy of reactants. I hope you have understood through these two expressions that how come Sp is greater than Sr and how come Sp is less than Sr, depending upon any chemical reaction, my dear friends. If I give a general chemical reaction here, my dear friends, you can tell me calcium carbonate is there, it's a solid, okay, and it breaks into calcium oxide, that is also solid, plus carbon dioxide, that is gas. We know that this is the reactant and these are the products. Okay, entropy of the reactants, okay, it will be very, very less because it is solid. Yes, but look at the product. In product we have both solid and gas. That means the entropy of this solid, which is a product, will be less only. But this will increase the entropy. This gas will increase the entropy from product side. So my dear friends, tell me, on reactant side, what will be the entropy? It's a solid, entropy will be very, very less. But on product side, at least we have one gaseous mole, carbon dioxide, that will increase the entropy from the product side. So for this reaction, I will write down Sp is greater than Sr, my dear friends. So entropy of this particular system will increase. So here for this reaction, delta S will be positive, my dear friends. Sp is greater than Sr. So my dear friends, I hope you have understood now with respect to some chemical reactions also, what can be the value of delta S? Delta S is positive, yes, when entropy of the products is greater than entropy of reactants, and entropy change will be negative when the entropy of the reactants is greater than the entropy of products. I hope you have understood. Please make note of this. Let's take few examples to understand now what will be delta S for these reactions, my dear friends, or these physical processes. Okay, so my dear friends, what is important here we need to understand. We know that delta S is equal to Sp minus Sr, and we know one more thing here, that is when Sp is greater than Sr, at that time delta S is positive, correct? Entropy of the system will increase. Okay, when Sp is less than Sr, delta S is negative. So my dear friends, we can easily tell on the basis of this. And one more expression which we have derived, that was basically order of entropy. Order of entropy. Okay, that was solid lesser than liquid and liquid less than gas. Okay, my dear friends. So now we will understand what happens to the entropy in this case. It's a chemical reaction here. We have reactants and we have products. In reactant we have only solid here. So we have only solid here in reactants. But in products we have solid, gas and gas. That means if we compare, here it is solid, here is also solid. Yes? So we cannot make any difference. But in product side we have gases also. Because of the presence of the gas on product side, yes or no? Entropy of the products will be more. That means, will it be the first expression or second expression? First expression. So for this, Sp will be greater than Sr, my dear friends. Because on product side we have gases, and on reactant side we have only solid. So entropy will be less and entropy will be more here. So Sp will be greater than Sr. When Sp is greater than Sr, obviously what will happen? This is greater than this. The delta S value will be what? Positive. So here delta S is positive. So the entropy of the system will increase, or the entropy increases. Correct? Let us take on the second now. It is not a chemical reaction, it's a physical process. You are going from liquid to solid, my dear friends. Who has more entropy? Liquid has more entropy or solid has more entropy? Liquid has more entropy. That means this guy has more entropy, my dear friends. Yes? So here my expression will be delta S is equal to S. Okay? What is this? Solid. So for solid I will write down final minus, what is initial? The liquid. So S initial. We know that for the water solid entropy is very less. So that means S final is very less. But for liquids entropy is more as compared to solid. So which factor is greater? Si factor is greater or Sf factor is greater? Sf factor is greater, my dear friends, or Si factor is greater? Si factor is actually greater. Why? Because this Si belongs to this. So entropy for the liquid. When liquid changes into solid, we have here Sf, entropy of the final product. This is initial and this is final. Which one is greater? Liquids have more entropy, so this is greater than this. That means here Sf is less than Si. Okay, so I will write down here Sf is less than Si. Correct? So the obviously Si is greater, so we'll have a negative value here. That means entropy decreases for this. Then we have hydrogen gas. How many moles we have here? We have 1 mole of H2 gas here. Okay? And here we have 2 moles of hydrogen atoms or hydrogen gaseous atoms. So remember always one thing, when number of moles, okay, when number of gaseous moles increase, entropy will also increase, my dear friends. So have a look here, my dear friends. We have here only 1 mole of hydrogen gas, and here we have 2 moles of hydrogen gaseous atoms. So 1 mole, from 1 mole to 2 moles we are going, my dear friends. If this is, let us suppose, our reactant, so this is Sr and this is Sp. So tell me, my dear friends, Sp and Sr, out of them, which one is greater? More number of moles, so more will be the entropy. Yes? So Sp is here greater than Sr. It's also a chemical reaction, but this was a physical process, that's why I used final and initial. But here it's a chemical reaction. So delta S is equal to Sp minus Sr, my dear friends. And we know that Sp is greater, so the delta S will be positive. That means entropy increases, my dear friends. So entropy is increasing. Dear friends, for a reversible reaction or a reversible process, my dear friends, what is the delta S relationship with Q and T? Q is basically the heat, absorbed or evolved, depending on the plus and minus sign of the Q. And T is basically the absolute temperature, the temperature measured in kelvins. Okay? So what is the relationship for a reversible process? That's this. Delta S system, that is entropy change, is equal to Q upon T. For which process? For the reversible process, my dear friends. What is the meaning of this? Let us understand. Okay? If we look at the temperature, it should be an absolute temperature. What is the meaning of absolute temperature, my dear friends? The temperature measured in kelvins. Measured in kelvins is your absolute temperature. And this Q is basically the heat. Okay, heat absorbed or evolved. If it is basically, let us suppose heat is absorbed, then I will write down plus. If it is basically, evolved, then I will write down minus. So heat can be either absorbed or evolved. But you need to understand it basically. Here the heat will be absorbed basically. Why? If I tell here heat absorbed. Let us suppose we have the temperature, it's an absolute temperature measured in kelvins, and we know that, let us keep this temperature constant, my dear friends. Okay? So at constant temperature, we will supply the heat to the system. Okay? So let us suppose this temperature is constant. So at constant temperature, I am supplying the heat, okay, to the system. Okay, in a reversible process. At constant temperature, I am supplying the heat to the system. So what will happen to the entropy of the system? Entropy of the system will increase, my dear friends. So let us write down this term T. Okay, the meaning of this expression. At constant temperature, heat is supplied to the system. Okay, so when heat is supplied to the system, I will write down heat absorbed by system. At constant temperature, heat supplied to the system. Okay? In a reversible process will increase the entropy of the system. So my dear friends, this temperature is constant for you, and this constant temperature, let us suppose you can keep it as 25 degrees Celsius as constant temperature, or if you don't want 25 degrees Celsius, you can keep it as 100 degree also as a constant temperature, but don't change the temperature. If you are fixing the temperature, let us suppose, if you fix the temperature by 25 degrees Celsius, then keep heating the system at that 25 degrees Celsius temperature only. Then observe what will be the entropy change in the system. entropy of the system will increase. Yes, if you heat the system at constant temperature of 60 degrees Celsius, let us suppose, or 60 Kelvin, let us suppose, because absolute temperature is taken in Kelvin. Okay, you can convert degree Celsius into Kelvin, that's not a big thing. So let us heat the system at constant temperature 60 Kelvin. So 60 Kelvin is a constant temperature. At that temperature, you are supplying the heat to the system, and obviously the entropy of the system will increase, my dear friends. That's exactly what I want to tell you. So obviously at constant temperature, heat supplied to the system in a reversible process will increase the entropy of the system. Please make note of this. So dear friends, now let us talk about the second law and third law of thermodynamics. We have already discussed the zeroth law and first law of thermodynamics. So these two laws are related to the entropy. Please remember that. Second law and third law are related to the entropy. Have a look. According to the second law of thermodynamics, the total entropy of universe, okay, which is equal to, you should remember, this is equal to delta S system plus delta S surroundings. That is the total entropy of the universe. Must increase in every spontaneous process. I already discussed with you I have discussed this particular fact. What is a spontaneous process? The process which takes place by itself without the assistance of external agency. But you know, you're very clever, you know that differential amount of energy is required there. So for spontaneous process or spontaneous reactions, which we have already discussed, yes I know, like water flows from higher concentration to lower concentration, yes, or we have discussed about like a rock being pushed and it rolls down from the top of the mountain to the foothill, yes. So we have discussed many spontaneous processes in previous class. So for all those spontaneous processes, my dear friends, the total entropy of the universe, look here, the total entropy change of the universe is equal to delta S system plus delta S surroundings, and this total is equal to or greater than, what is the factor here? It is greater than 0. That means the total entropy of the universe, when it is greater than 0, understand that it is positive. When it's positive, that means it is increasing. That means entropy, total entropy of the universe is greater than 0. That means it is increasing, my dear friends. It's on increasing side. So remember that factor. The second law of thermodynamics, the total entropy of the universe is always positive. It's always on the increasing side. What is the meaning of that? That means the disorder in the universe is increasing day by day. Yes or no? And you know that the total entropy of the universe is equal to entropy of system plus entropy of surroundings, and this is equal or greater, it's greater than 0, my dear friends. Once again I am telling you, the total entropy of the universe is equal to entropy of system plus entropy of surroundings, and this expression is greater than 0. Greater than 0 means positive. That means entropy of the universe is increasing. That is the second law of thermodynamics. Let us go for now third law of thermodynamics. What is this all about? The third law of thermodynamics is the entropy of a pure crystalline substance at absolute 0. Okay, temperature, that is 0 Kelvin, is 0. What is the meaning of this? Have a look. If we take this expression, this second law, my dear friends, I will take a pure crystalline substance. I have a pure crystalline substance. Okay, so this is with me pure crystalline substance. Now you will be thinking, what is this pure crystalline substance, my dear friends? You can take pure NaCl, sodium chloride. Okay, that is a pure crystalline substance. What happens when this substance is exposed? If this pure crystalline substance is exposed to 0 Kelvin temperature, Okay, 0 Kelvin temperature is basically minus 273 Kelvin. Sorry, minus 273 degrees Celsius. So 0 Kelvin temperature is minus 273 degrees Celsius, my dear friends. So when this pure crystalline substance is exposed to 0 Kelvin temperature, what happens? Then its entropy turns out to be 0. If you take any solid substance, any crystalline substance, entropy is there. It's always there. Let us suppose if you take sodium chloride, magnesium chloride, any crystalline substance, there will be always an entropy, disorder will be always there. Like molecules or atoms or ions will be vibrating, so disorder is there. Randomness is there, but very less, okay, in case of solids. But if you expose or if you apply, how much of temperature you are applying to the pure crystalline substance? You are exposing it to 0 Kelvin, which is practically impossible. But let us suppose if you are exposing it to the 0 Kelvin temperature, that's equal to minus 273 degrees Celsius temperature. Then what happens in this pure crystalline substance? Then the entropy turns out to be 0. Then your pure crystalline substances will have 0 entropy. That means disorder will become 0. But at which temperature? 0 Kelvin. Yes? Normally if you keep, let us suppose this is sodium chloride crystal. At room temperature, the ions Na plus and Cl minus ions will be vibrating. Then I am taking this NaCl and exposing it to 0 Kelvin temperature, minus 273 degrees Celsius. What happens? Even the vibration will also stop. No more vibrations. So when no more vibrations, no more chaos, no more disorder, no more indiscipline, yes, and no more randomness, that means entropy will not be there. So entropy will become 0. So that is what we call as third law of thermodynamics. And obviously this is practically impossible to arrange this minus 273 degrees Celsius temperature and all. So I hope you have understood now second law and third law. Second law was that the total entropy of the universe will be always greater than 0, which means it will be always on the increasing side. And the third law was basically, if you expose a pure crystalline substance with some vibration, some entropy will be there. If you expose it to the 0 Kelvin temperature, then all the entropies will cease to exist. It will be having a 0 entropy at 0 Kelvin temperature, okay, which we call as absolute 0 temperature, my dear friends. And that is the third law of thermodynamics. Please make note of this. Dear friends, let's look into the question, okay. While we are doing oxidation of iron, iron is oxidized and I am getting iron oxide. So let us see in this chemical reaction what happens. The entropy change is negative, my dear friends. So let's write down my first point here. That is delta S system. Because during this process, the entropy change is negative. So it's an entropy change of the system is minus 549.4 joule per Kelvin per mole, my dear friends. So joule per Kelvin is the unit of the entropy change. Because we have already done this, entropy change is equal to Q upon T. Heat is measured in joules and temperature in Kelvin. So joule per Kelvin is the unit of entropy change. Simultaneously, at what temperature you are carrying out the process? The temperature given to us is 298 Kelvin. Okay. In spite of negative entropy change of this reaction, why the reaction is spontaneous? So my dear friends, if we look at the second law of thermodynamics, we discussed that second law of thermodynamics. According to second law of thermodynamics, my dear friends, for a spontaneous process, according to this law or reaction, what happens? Delta S total is equal to delta S system plus delta S surroundings is greater than 0. So for a spontaneous process or reaction, my dear friends, for a spontaneous process or spontaneous reaction, what happens? The total entropy change of the universe should be greater than 0. But if you look at the entropy change here, my dear friends, entropy change of the system is minus. Minus means it is less than 0. But if you try to analyze this problem, you will find out this is the entropy of the system, which is negative. Okay? When we talk of the spontaneous process, my dear friends, look here. When we talk of spontaneous process, what should be the value of the total entropy of the universe? Greater than 0. That is positive. Yes? But this is the entropy change of the system. Are you following or not? If this value will come out to be positive, then my reaction is spontaneous. But only which value is negative here? Delta S system. That means only this part is only negative. So I have to calculate total. What is the total change, my dear friends? Total entropy change of the universe I have to see. So let us go further and understand this thing. This is already given to me. This is how much? Minus 549.4. So this is given to me as minus 549.4 joule per Kelvin. So I have to calculate this thing. So here I have to calculate entropy of the surroundings. Then I have to take these two values. Then only I can decide whether the reaction is spontaneous or not, my dear friends. Don't decide the reaction is spontaneous on the basis of this delta S system value. You have to decide whether reaction is spontaneous or non-spontaneous on the basis of delta S total. Delta S system is given to me, but delta S surroundings is not given to me. So let me find out what is delta S surroundings, my dear first. Now look here, my dear friends. This expression is already given to us. If you remember, delta S system, we already know it's Q upon T. Yes, that is heat is absorbed by the system. If I want to write down it for delta S surroundings, it will be, my dear friends, minus Q upon T. Do you agree with me? It will be minus Q upon T. Because if the system will absorb the heat, the surrounding has to lose the heat. So this will be my expression, my dear friends. Try to understand. And we know that this chemical reaction is taking place at, at the atmospheric pressure, let us suppose. If this chemical reaction is taking place at atmospheric pressure, my dear friends, then in place of this Q, I can write down QP. That means atmospheric pressure will be constant, so I can write down QP. Let us suppose this reaction is taking place at constant atmospheric pressure, that is 1 atmosphere. So I can write down QP, and here also I will write down QP. If you remember, last time I told you about QP. If you remember, QP is equal to delta H. The heat absorbed at constant pressure is equal to delta H, my dear friends. So that means in place of now QP, I can add on delta H. Change in what? Enthalpy. You can take it as a standard enthalpy of reaction as well, my dear friends. If it is minus QP, then we will have minus delta H R naught. Let us suppose here for delta S surroundings we have minus QP. So I will get minus delta H R naught. So let us calculate now here delta S surroundings. That's equal to, my dear friends, minus QP upon T. We know that QP is equal to delta H R naught, correct? And here we don't have QP, here we have minus QP. So obviously this will become minus QP is equal to minus delta H R naught. So I will write down here minus delta H R naught upon T. And we know that delta H R naught, that is given to us, it's minus 1648 multiplied by 10 to the power 3 divided by T. T stands for, here the temperature we are taking 298 Kelvin. So 298 Kelvin, my dear friends. So this is our expression, my dear friends. We have to simplify this thing. So when you simplify it, my dear friends, you will get a value like this, 5530. But before this particular thing, I want to tell you some important factor here. This is minus 1648 in 10 raised power 3. This is the value of delta H R naught. And in formula we have already minus here outside. So obviously we have to write it like this. This is the value of delta H R naught. Yes, this is the value of delta H R naught. But minus is outside, so we have to mention this minus. So try to understand this particular factor. So it will become plus. So you will get a plus 5530. Okay, this will be basically delta S surroundings. So it will be in joule per Kelvin per mole. So this is the value of delta S surroundings. Now I have to put this value here and find out what is delta S total. If delta S total is greater than 0, that means positive, then reaction is spontaneous, otherwise not. So let's have a look now here. Delta S total is equal to, my dear friends, delta S system. What is that? Minus 549.4 joule per Kelvin. And what is delta S surroundings, my dear friends? Delta S surroundings is 5530 joule per Kelvin or per mole. Right? Now you know that this is a bigger number and this is a smaller number here. It's 549.4. So obviously the value will be positive only, my dear friends. So if you do its calculation, you will get the value of 4,980.6. 4,980.6. I have already calculated this thing, so you will get this particular value, that is joule per Kelvin. Okay. So now, my dear friends, this value is positive. So delta S total value is positive here. Yes. So when delta S is positive, delta S total is positive, that means it is greater than 0. So here, my dear friends, delta S is positive. Have a look here. It means delta S, sorry I should mention total, delta S total is greater than 0. That is, the entropy of the universe is greater than 0, and obviously then I can tell it is a spontaneous process. So it's a spontaneous reaction, my dear friends. I hope you have understood. Okay, that means your spontaneity of a reaction does not depend upon the delta S system, or it does not depend upon the delta S surroundings. It depends upon the total of delta S system and delta S surroundings. Together their value, if you put, if it is greater than 0, understand the reaction is spontaneous. And we have finally proved it, yes, definitely the reaction is spontaneous because the value is positive right out here. I hope you have understood. If I revise it for 1 minute, you will find out we took one reaction, we did oxidation of iron, we got iron oxide. And finally the entropy change for the system was given to us minus. Yes, and we know that according to second law of thermodynamics, the entropy change, total entropy change of the universe should be positive. But I am getting here negative, and this is not for the total entropy of the universe, this is the total entropy of the system. It's negative. And then they are asking us that if the entropy is negative, why the reaction is spontaneous? But my dear friends, this is not, we are not looking for the entropy of a system, we are looking for the total entropy of the universe. And finally, entropy of system was given, entropy of surroundings was not given. And this total should be greater than 0, then delta S will be positive and we will get the reaction as spontaneous according to second law of thermodynamics. This was given and then I calculated delta S surroundings. How I calculated? We know delta S system is Q upon T, and delta S surroundings will be minus Q upon T, exactly opposite of this. Heat will be absorbed, heat will be lost. And you know that this reaction is taking place at atmospheric pressure. So that is 1 atmosphere, so pressure is constant. So when pressure is constant, I can take it as QP. Okay, so QP we know, already we have done it previous time, that heat absorbed or heat lost. This is here, heat lost at constant pressure will be equal to minus delta H R naught. So it's related to delta H, enthalpy change of the reaction. So finally delta S surroundings is equal to QP upon T, that's minus, and this term can be replaced by delta H R naught. Okay, minus is already there and the value of delta H R naught is also minus, so minus minus plus. So finally you are getting 5530 joule per Kelvin per mole as delta S surroundings. Finally, when you get this delta S surroundings, you can put it here. So this and this should be greater than 0, means positive. And I found it that it was plus 4980.6 joule per Kelvin, that is a positive value. So delta S total is positive. That means delta S total is greater than 0. That means the reaction is spontaneous. I hope you have understood, my dear friends. Please make note of this. Take care of yourself. Catch you in the next class. Have a great time. Thank you.